Exercise 1022 is asking you to think about synthesis with these alkynes in order to make aldehydes and ketones. Now already, if you've already learned the reactions, when you hear those key words, you should say, oh, aldehydes and ketones with alkynes, those are the hydration reactions. The acid-catalyzed hydration and hydroboration oxidation, because those add the H's and the OH's that then undergo ketoenol tautomerism to give me the alkynes or the aldehydes. Now, if everything I just said sounds like a different language, go back, watch the videos on ketoenol tautomerism, watch the videos that walk through how to predict the products of acid-catalyzed hydration and hydroboration oxidation, and memorize the reactions first. Only then will these exercises make sense. So here, you'll notice that the number of carbons doesn't change. You have 1, 2, 3, 1, 2, 3 in this chain outside of the cyclohexane ring. But what does change is that here we have 2 pi bonds. 1 sigma bond, that's the first bond you ever form, and then 2 pi bonds after that. Whereas in our product, we only have 1. Also, here, we don't have an oxygen, or we have an oxygen in the product that we don't have in the beginning. So we know we're going to have to do some sort of addition reaction. Well, what would you want to add on? We want to add on some type of an oxygen. The way that you can form these aldehydes and ketones, this is a ketone, because you have a carbon double bonded to oxygen, bonded to a carbon on both sides. So the way that you can form those from alkynes is by doing hydration. Now you'll notice that we have 2 carbons here. The one at the end is primary and the one in the middle is secondary. The oxygen, so this was primary, this is secondary, the oxygen went to the more substituted one. That's Markovnikov addition. And so how can you put an oxygen onto a triple bond in a Markovnikov way? That's acid-catalyzed hydration. Water, H2SO4, and mercuric sulfate. And that is really just a matter of remembering. The reaction from earlier. Acid-catalyzed hydration is this here. You can see that it turns an alkyne into a ketone by adding a double bond to an oxygen on the more substituted carbon. So Markovnikov addition. And we've talked about the mechanism for that, both in terms of adding the H and the OH in a Markovnikov way. You drew the mechanism for that in the previous chapter, and then the ketoenol tautomerism that happens afterwards. But anytime you see an alkyne turn into an aldehyde or a ketone, you should think, okay, it's either going to be acid-catalyzed hydration, if it's Markovnikov addition, if the double bond to the oxygen is on the more substituted carbon, or hydroboration oxidation, if the double bond to the oxygen is on the less substituted carbon. So here, for example, you'd see an alkyne, you'd say, okay, alkyne reactions, they're going to be addition reactions. What are we adding? You'd see the oxygen there. Okay, how do you add an oxygen onto an alkyne? Well, you could do acid-catalyzed hydration or oxymercury or hydroboration oxidation. You know that it's not ozonolysis because you have the same number of carbons. So in both of these you have sort of a 5-carbon chain with 2 methyl groups on carbon number 4. So if you do ozonolysis, you cut the triple bond, and so you would saw a carbon off of the molecule. But since we have the same number of carbons, the only other way to add an oxygen onto an alkyne is to do hydroboration oxidation or acid-catalyzed hydration. And that gives you an aldehyde and a ketone. So what we see here is that the double bond to the oxygen is on the carbon at the end. Now notice, this is primary and the carbon in the middle is secondary. So the double bond to the oxygen went on the less substituted carbon. The hydrogens went on the more substituted carbon. That's anti-Markovnikov addition. That means that you have to do hydroboration oxidation here. And so for alkynes, make sure you use a dialkylated borane. like 9 bbn. But in general, any two alkyl groups, so hydrocarbon chains, bonded to a boron that has just one hydrogen would work. And then follow it up with hydrogen peroxide and sodium hydroxide. And so you would have to remember that. If you have this reaction memorized, if you have this reaction memorized, which we had up here too. If you had this hydroboration reaction, oxidation reaction memorized, you would know that as you go from you can turn an alkyne into an aldehyde. That's a carbon double bond to oxygen, that it has a hydrogen on one side. You can do that by doing hydroboration oxidation, using this recipe that we just wrote down. Okay, so what is the overall message from this exercise? I mean, there's the knowing how to change these specific molecules, but the molecules on the test won't be the exact same. So what is the big picture that you can learn from this and apply to any molecule or a similar problem on a test? And that is that if you see an alkyne turning into an aldehyde or a ketone, you know that it's acid-catalyzed hydration. If you see an aldehyde or a ketone, you should think, okay, I can make that from an alkyne. And the only other thing you have to consider is whether to do acid-catalyzed hydration, if you want Markovnikov addition, or hydroboration oxidation, if you want anti-Markovnikov addition, if you want the aldehyde, the double bond to the oxygen on the less substituted carbon.